right now? Okay, so we're talking about what defines a collision, and the group of very, very hardy souls here learning physics on a Saturday, Friday, whatever day it is, afternoon, are a little bit unsure. And I gave the hint that we're talking about collisions when we're talking about conservation momentum. What is the condition for momentum to be conserved?
No external forces
No,
acting on.
exactly. No external force. And I would say that's what characterizes what we call it, physicists would call a collision. So like this thing, for example, I'd call this a collision, even though you'd be like, what? That's an explosion. Explosions are collisions because all the forces are internal to the system. And I'd go as far as saying that a ice skater pulling her arms in as she spins in a pirouette is a collision in that sense, because all the forces are internal to the system. And like, isn't that just one object? Well, she's got like a torso and arms. That's what I would say. So that's actually like 3 objects, right? So the idea is that there are only those forces that are internal to that system that is making the change in the motion happen, and momentum is necessarily conserved. So always coming back to the idea that collision is always true when all external forces are equal to 0. And of course, for rotation, it means that the external torques equal to 0 is the reason why we're even talking about a collision or a conserved momentum situation. Okay, so we have here P, and then of course here it would be L, and again these are vectors conserved. Okay, so angular momentum or linear momentum are conserved in those situations. Okay, so that's the big thing. And of course, on the flip side, and this is where you guys tend to get trapped, is that you have a tendency to make certain conclusions about energy here, okay? And momentum is conserved, okay? Now, is kinetic energy conserved in linear collisions?
Depends on the collision.
Depends, right? Can sometimes the kinetic energy actually become smaller?
Yes.
Can sometimes the kinetic energy get larger?
No.
Yes. Like this would be an example, right?
Oh,
So,
I was thinking total energy, sorry.
yeah, but this energy of the system, of course, the total energy of the universe will always be the same no matter what, right? You know, as long as you consider the energy and mass together, and E equals mc squared and all that.
I was thinking of the system. How can the total energy of the system increase if it's
right?
internal?
It depends on what you. So, for example, you might have a. So again, we would say now technically, you're right, because when we have this rocket flying along, we're not thinking about the fact that there is actually an explosive in the middle, or if we were going to be the poor man's rocket, 2 carts on a track with a spring in between that's pushed together, and then as they're moving along, right? There's energy stored in that spring. But what we mean by that is total energy is conserved, true, but not kinetic energy. So kinetic energy can go down, up, or stay the same. But momentum is conserved. And the same thing applies for angular momentum. So if you have an angular momentum situation, you have a rotation situation, and that situation, you can, as long as the torques are all internal, you'll definitely have your angular momentum conserved. That applies to and the thing I mentioned was like a turntable, and then somebody drops like a spinning disc on top of it, and then angular momentum is conserved. Or the spinning ice skater, or some other situation, a comet approaching the Earth, those kind of things. In those kind of situations, angular momentum is conserved, but kinetic energy is not necessarily conserved. And it can go up, it can go down, it could sometimes stay the same, but it doesn't necessarily go the same way. All right, that was kind of generally talking about it a little bit. So we should maybe now go and review something specific. Do you want to try that example? I'm going to look if we have what we have here for our FRQ. I don't think it's super helpful. Unit 5, we've got a snowball. Okay. So, hey, maybe we'll do that. So let's just kind of work on this problem. This is unit 5, progress check, which means it's corresponding to rotation. You guys mentioned that rotation freaks you out, so let's try it, okay?
Mm-hmm.
Okay, here we go. So we've got our little intro here. We'll take ourselves a little picture. And here we go. Okay, and just turn this here. And so we have a kind of a hill. It's very steep, actually. 30 degrees doesn't seem steep, but it's extremely steep when you're actually existing in real life. It's 2 meters tall. We've got a snowball up here that's starting this process right there. And here we go. And it has a mass of 250. There we go, 250 grams. And a radius of 4 centimeters. Whoop. R equals 4 centimeters. And while we're at it, let's get those converted into standard units right away. Always a good idea. And now we've got this thingamajigger here. And obviously, this thing's going to roll down the section of the incline. And the question we have here, first of all, is it'll rotate, right? Why does it rotate?
Because there's friction.
Because there's friction. Friction is key. So you can't forget about the friction. Friction is important. So when we draw in the forces, which I don't think they're going to ask us to do, but just to review, this would be helpful for us, right? What are the forces acting on this thing?
Gravity.
Fg, points downward. And for a rotational situation, it is helpful to draw it in where it grips. Like where does it actually attack? Not the point of attack, the point where it actually acts on the object, because we'll need that for our torque. Okay, so this grips there, fine. And the second force?
Normal.
Normal force. And normal force acts where?
Surface, like
Surface.
Perpendicular to the surface.
It's perpendicular to this surface, so it kind of goes in this direction. This is Fn. There we go. And what else?
and friction.
The force of friction?
Friction force. Okay, and the friction force goes in this direction. Good. And is this a kinetic friction or a static friction?
Static.
It is a static friction because we're not slipping, which is ironic. We label it FFS when it's not slipping. When it's slipping, we label it K. Okay, cool. So here's a trick question. If our snowball is making contact here, how do we know it's acting this direction and not that direction?
I mean, I think of it as that as the torque causing force, and as it rolls down clockwise, and it has to be, do you know what I mean?
Sure, it has to start rolling. We know it's going to start rolling, so that's actually not a bad way of thinking about it. It's going to act on this lever arm right here and actually create this clockwise rotation. In general, this is not necessarily true. So when you have a wheel like this, for example, on a car, right, or it's powered or something like that, you can have a friction force in either direction dependent on what's happening. So for example, if you imagine this is actually attached to a whole car, right? Exactly, and this thing is actually moving up the slope. It's standing still, and now it's going to start moving up the slope. Of course, in that case, we need to make this thing turn this way. In that case, the friction force actually has to be pointing downhill in order to make that happen. Do you guys follow that? Okay, so the direction of the friction, apart from it being perpendicular to the lever arm here, and of course being along the direction of the surface, because friction force always acts parallel to the surface, and normal force always acts perpendicular to the surface. That's what those two contact forces do. The direction is not necessarily one or the other. And that's always true of friction forces, right? When we have a block sliding, right, along a block on a table, depending on which direction it slides, the friction force is either one. But you could also power it, like push it along or slow it down, and then you could have a friction force in either direction. Okay, sweet. So we got that figured out. And now they're going to ask us a question about it. So and if you were faced with this on Monday, they're not going to ask that, right? Because it's a kind of a little bit too simple. But let's say they asked, how does this thing roll? What force causes the snowball to roll? Your answer would be the friction force, right? And then we could kind of go through the conversation we just had and spell out why it would have to be acting upslope in order to create a clockwise roll. And then you could also be asked, explain why the other forces do not create torques. Okay, so they say they could ask them like there are 3 forces acting on this snowball. Hey, we're just developing a good question. I like this question. So they've got 3 forces acting to explain which force is creating a torque and in which direction it must act based on the situation. We just answered that. Can you explain why the gravitational force does not create a torque?
Because it's acting on the center of the.
Good.
Or
We
on
could
the
consider
center
it to be acting on the center. We could be all like, well, how it's not actually acting on the center because it's acting all over. But we're allowed to do that. That the center of mass is where a gravitational force acts. So that means it has a lever arm of 0. Sweet. Okay, cool. Now, how about the other force? What's the other force?
Normal.
Normal force. Why does the normal force not create a torque?
Because it's perpendicular.
Uh,
Like it's at
That is definitely something that you'd be in big trouble with your reader, because I think you mean the right thing, but you said exactly the wrong thing. Because when we think about perpendicular, so you didn't say perpendicular to what? And when we're thinking about a force creating a torque, it's also about its angle in respect to what?
that point of rotation or the axis or
The axis or the lever arm. Okay, so when we draw the lever arm connects the point of rotation to the action point where you have the force basically acting, right? So when we put in that lever arm, right, here it is. There it is. Ah, shit, this is in green is terrible. I'm gonna go with red here, better. So red. Ah, it's horrible too. Okay, I'm gonna just, okay, this is gonna make a mess, maybe, but we'll just do it. Okay, so here we go. So here we go. Okay, we can do this. So here comes that little lever arm, and it comes from the center of rotation, right? And it's a vector. The lever arm is always a vector. Does that show up at all? It's a red arrow coming from the center. Our vector. There we go. That's horrible. Okay. Anyway, and if you take a look at Fn, it is most definitely not perpendicular to the lever arm, right? So it has an angle of what to the lever arm? Trick question. Nobody wants to answer. Is it 0 degrees?
It's 90 degrees, right?
Nope.
180.
It's 180, right? So
Let's
the lever arm points down, right? Because you go from the point of rotation to the point where we're gripping, and the normal force goes the other direction. Okay, so remember, torque is R, this vector, cross F. Okay, and even though this terrifies the children a little bit, there are 2 aspects to this. Right? So the first one is that the magnitude of torque is equal to the magnitude of R, the magnitude of F, and the sine of the angle between the 2. Agreed? And then the direction is determined according to the right-hand rule. Okay? Where your fingers point in the direction of R, your curl is in the direction of the force, the first, the second, and then the last one, the thumb, indicates the direction of the torque. So that's always how you find the direction of a cross product. Boop. And that's why we kind of, threw that baby out of the wagon. That doesn't sound good. So we ditched that whole like unit 4 and 5 thing in magnetism. That's gone, but we had a bunch of cross products, right-hand rules, and that's why they're in there, because there's a bunch of cross products. But here the same thing applies. Now, coming back to why R cross F is 0 in this case, the angle's not 0, the angle's 180, and of course sine of 180 is 0.
Okay.
Okay? So, but you wouldn't have to say that. You could say the lever arm is parallel to the normal force. Okay? And therefore the torque of the normal force is 0. And you could vice versa say the torque created by the friction force is equal to the magnitude of the force of friction times the radius, because the friction force is perpendicular to the lever arm. Okay, so that'd be a good way of explaining why that's equal to that and why it's non-zero. And for FG, the same thing is a similar thing is happening, but FG in this case, of course, is 0 for a different reason. And that's why this is a fun problem, fun for like in terms of thinking about it, because there R is 0, right? Both have F non-zero, both FG and Fn have a non-zero F, but FG has R 0 and Fn has sine theta 0. So that's why both of them create 0 torque, but for 2 different reasons. Okay?
Mm-hmm.
You feel calmness coming over you about rotation or not yet? Not quite, huh?
Not yet.
Not yet, actually. Thank you for asking. Quite. So let's see. Now they say calculate the linear acceleration of the snowball as it rolls down the inclined section of the roof. At this point, you're like, what? So there's going to be one of 2 things that happens. Either you do this completely wrong, which is probably what's going to happen, or you don't do the problem. And there's a third possibility, you actually do it right, okay? So it's really easy to have a problem like this be like, oh man, I totally got this. It's mg sine theta, it's gonna be the force, and that's gonna be equal to ma, a is g sine theta. Why is that wrong?
Didn't, because you didn't take into account the friction force?
Correct. I am quite happily blocking that to make sure you missed that, but you didn't. Good job. So the friction force is actually going to reduce the acceleration. Okay, so in this case, what we started with is still good. So linearly, right? We still have, let's do it this way. Let's actually just write it out. Remember, Mempke recipe, right? Fg x, right? Minus Fs, correct? Right?
Mhm.
And that's equal to ma. Definitely true. We're all good. Happy? Good. So now we could have a second situation where we could write in a y direction force, but it's kind of silly, right? Because all we're going to get is that Fn minus Fgy equals 0,
Mm-hmm.
right? And that's super unhelpful. But we do have a rotational one, and that's really helpful. So rotational one, I'm actually going to do it this way. So let's not write it down here. That's really messy. Wow, that's great. Great. So we're just going to write it up here inside the triangle. I think we have enough space there, so we can write it like kind of across here. Because I'm writing in black, I think it's going to be okay. Okay, so there we have, we already said what's creating the torque. It's FFS, right? And we said the torque is that times R, right? And this is equal to I times alpha. I should have asked you about that, but straightforward. So all we're doing is here, we're applying Newton's second law for rotation. Yeah? So we have torque equals I alpha, net force equals ma. Here, net force is equal to 0 because in the vertical direction, there's no acceleration. Okay, you guys cool?
Yeah.
Okay, so this one is totally useless. We're not interested in that because all we would get is that Fn equals mg cosine theta. Not that interesting, but here's some interesting stuff happening. So first of all, let's think about FFS. We have friction force. We always might be interested and tempted to say, oh, this is equal to USFN, right? Is it equal to that?
No.
Not
Depends.
necessarily, right? Probably not, right? It's definitely going to be smaller or equal to that. Okay, we don't know it's equal to that because they're not saying the snowball is accelerating at its maximum possible acceleration without slipping. Okay, and that can happen if you make this thing steep enough, right? Obviously, if this wall was vertical, the ball would just fall. It wouldn't actually rotate, right? And if you go somewhere in between, well, I'm kind of turning the wrong way. Like if you go this, like a big angle like that, like the friction force would reach past its maximum possible value because this coefficient of friction is only so large. And at that point, the ball would just start slipping rather than rotating and would just kind of like an avalanche just fly down that hill without rotating. Okay? So that's not equal to each other. And let's take a look at this thing and think about what do we know. We've got FFS in both of these. That's definitely an unknown. And it looks like we have two unknowns over here, A and alpha. Is that true?
Well, A and alpha are related.
They're related, exactly. So alpha and A are bound together by this radius r. So it's always important to remember breathing, all that thing, right? It's always important to come back to what do we know linear, what do we need rotational, and then sometimes there are linking equations between the two, right? And we have like x, right? Theta, right? Theta r, v, omega, omega r, a, alpha.
Can you move it down a little? Okay.
Alpha r, yeah. So those are kind of our linking equations. And for each one of the motion equations, the angle that you move through times the radius for circular motion, right, would be just the distance you move through. And you can use the same thing for differentials, okay? And then the speed is omega times r, okay? A is alpha times r. That's a linking equation putting the two things together, okay? So if we do that, now we can come back to our set of equations and say, aha! You don't have to say it with such vigor, but you could. So then we have this thing over here and say A divided by R. There you go. So we've got now one less unknown. Now look at that. We still have I. That's a problem, right? Now this thing is a sphere, we assume. Although you could make a snowball that's more like a snow cylinder, right? But this one is a ball, so it's a sphere. So they give us the moment of inertia for a sphere? They don't, do they?
No.
No. And in the moment of inertia for a sphere, is it? I have 3/5 mr squared in my head. Is that correct?
Sounds familiar, but
No.
I'll check.
Thanks for Googling that for us.
No problem. All right. A solid sphere is 2/5 mr
2/5.
squared.
Okay. That was close, but not good enough. So 2/5 mr squared is the moment of inertia of a sphere. 2/5 mr squared. This kind of ties back nicely to remember that problem we had with the beta mr squared idea and then plotting it. So there's always a factor here, and then it's mr squared, and the factor here has to be 1 or smaller, and 1 being an object that has all its mass located at the edge, like a hoop, and then if it's actually got a factor of 0, it's an object that's actually not rotating or has effectively all of its mass concentrated at the center. Okay, so then we can take this and manipulate it. So let's come back over here to our two equations. We're gonna scooch down a little bit here and plug that in. I'm gonna go with the red because I think that'll help us kind of distinguish what's happened here. So we have FFSR. We have here now I, which is 2/5 mr squared, A divided by R. We're just writing things down. We're remembering to breathe. Okay, it's important. And then we have the other equation here, FGX. We know that FGX is mg sine theta. There is that term that we were so confident and felt good about initially. Then we have FFS here. And then at the right side, we have MA. Okay, good. So let's take a look. The R's, I don't think we need to actually go through it because at this point, maybe we're wasting time to some degree, but maybe not, I'm not sure. So anyway, we have an R on the left side. We actually have one R over here. So these all cancel, they're all gone. And down here, nothing cancels right now. But now we have an expression for FFS, and we can plug that in there, and then we can solve it. Let's just do that because we're this close to the answer. And even though they're probably not going to ask that on the actual exam, I think it might be just, you know, character building to have done that again. So we have mg sine theta, and we can plug the whole thing in there. So this is minus 2/5 ma. And over here we have equal to ma. Now the m's cancel. It does not matter what the mass is, as long as it's not 0. Okay, stupid. It won't accelerate by gravity if the mass is 0, and the radius can't be 0 either because we canceled that out earlier. So but that's obviously true. Like, what the heck is a snowball with no mass and no radius? Not a snowball. Okay, so we look at this then and say, okay, well, this means then we have g sine theta equals 7/5 a, and then of course a is equal to 5/7 g sine theta. There we go. Did I do that correctly? Besides not getting this on the screen? There we go. Okay, you guys follow that? Did I do it right? I think I did. You guys okay? Did I scare the children? Are you guys with me? Or both? You're with me? Okay. Now, they're not going to ask that because I think it's too derive-y, right? Yeah, let's just leave it at that. Okay. And again, so the last tip, and I sense despair. So just to counter the despair, remember that this is not for some reason magically more difficult for you than it is for the 100,000 other students that are taking the test on Monday. So just, you know, remain calm and just, you know, try to beat Team China. So remember, we have this year, I think, an advantage to some degree over Team China because we speak English gooder. So, you know, because they're going to have to answer all this stuff with words and sentences where there are less derivations, where maybe Team China is a little stronger at that. Just to take, you know, that into consideration. So we can do this. Hope that was inspirational.
Thank
Okay.
you.
You're welcome. Yeah. And just try to do what you can. Like, you know, a lot of stuff that we've seen is like, you know, attempts to use integration with, you know, integration constants is like the first point or even 2 points out of 3. And then the third point is actually for doing the integral correctly. You know what I mean? So do what you can do and figure out, you know, how much you can do. And if you can't do the whole problem, that's okay, because a lot of students will not be able to do all the problems. Okay, good. I will erase that. You guys are okay with this so far?
Mhm.
So we can keep going on this problem, or we can switch gears.
I think we can just keep going.
Keep going on the problem? Okay,
Yeah.
good. Okay, let's see it. Here we go. Question B. Calculate the linear acceleration of the snow as it rolls down the inclined section using conservation of energy. Calculate the angular speed of the snowball as it reaches the end of the inclined section of the roof. Okay, so this is a little bit of a different approach. Now we can approach this, we kind of did a kinematics approach, that's cool, right? But we can also do a energy approach where this is 2 meters height difference, right? We have this thing up here initially, right? It's starting at V equals omega equals 0, right? And then down here it's scooching along, but it's also rotating, so it's doing both, right? There we go. And we're saying, okay, well, what is its speed or angular speed at the bottom here? Angular speed, doesn't really matter. Okay, so at the top, what kind of energy do we have?
Potential.
Potential. What kind of potential?
Gravity.
Gravitational, obviously. So this would be mg, and technically it's delta h, right? Where this is delta h, right? Or 2 meters. And this would be m times g times 2 meters. How about down here? What kind of energy do we have down here now?
Translational kinetic energy and rotational.
Good. So I like calling it linear. It doesn't really matter. Or and then I think that is easier to abbreviate than TRA or something. So there we go. There's 2 down here, and these 2 should be equal to each other. Good. So let's just write those out. mg times 2 meters. Then we have linear is 1/2 mv squared, and then we have the rotational is 1/2 I omega squared. And again, we're not going to ask you to do that. The AP is not going to ask you to do that on Monday, but they could ask you to explain the process. Say, how would you use conservation of energy to find the rotational, the angular velocity at the bottom of the hill? And you'd be like, well, at the beginning of the process, it has gravitational potential energy. At the end, it's all in linear kinetic and rotational kinetic energy. And keeping in mind that the rotational angular velocity and the linear velocity are related, we can then plug in and solve for omega or something like that. Yeah. So again, the connecting is this thing, V is equal to omega R. You can connect it this way. That's the way we want to connect it this time, because we're not interested in V, we're interested in omega. But we could also ask this problem in terms of what's the speed at the end, and then you'd obviously want to take this equation and look at it more in terms of this. But that's the same thing, and then you could solve the equation for V. Make sense? And obviously you need to, oh, the one thing I forgot to mention in my solution is you have to put in, say that we would plug in for the moment of inertia for a sphere. Okay, so you have to still say that. mg 2 meters equals 1/2 m omega r squared plus 1/2 I is 2/5 m r squared omega squared. Okay, now let's take a look at this. Now we can happily cancel out m. Watch out, this is 2 meters, right? So don't cancel out the m there. This is an m and this is an m. Okay, good. Now, can we cancel out the r's?
No.
No.
Yes. No.
There's no R over here, so watch out. There's only R's on the right side. And we have a tendency to think about these things in terms of that, so we would be able to cancel it out, but we cannot. So R matters here, so you cannot cancel that out. Not allowed to, okay? So let's take a look. But fortunately for us, we do know R. They gave it to us in the problem. They said it is 4 centimeters. Reminder, R is 0.04 meters. M actually doesn't matter. That cancels out. But we can now look at this and say we have here G times, I'm just temporarily going back to delta H. Sorry about that. So we have omega squared times 1/2 R squared. And this is 1/5 of an R squared. And 1/2 plus 1/5 is 0.7. Okay. I like, in this case, a decimal rather than 7/10. 7/10 seems not very intuitive to me. So you have 0.7 omega squared R squared. Okay. And then, of course, you can solve that for omega. Omega is equal to G.
Could you move the camera down a little bit?
Yep.
Thanks.
G delta H over 0.7 R squared square root. And then we can plug stuff in. It's still true that you can use 10 for G on this test. It's also true that you can leave off the units, so you don't have to carry the units. That's fine. 0.7, and then we have 0.04. You do have to make sure that you put them in standard units. So if you didn't put this in meters, then you could be in trouble at this point, and you'll find a rotational angular velocity that would be the correct one if that snowball was 4 meters large, not 4 centimeters. And that does make a difference, obviously. Okay, let's see what we get here. We got 20 on top there. We got 0.7 on the bottom. We got 0.04 on the bottom, square that. And then we take the square root, and I get 134 rads per second. I hope that's right.
Yeah, it is.
Good. Cool. All righty, that's A, B, C, D.
Could you explain one more time real quick how
Sure.
you found the moment of inertia for the sphere? And how
Oh,
you
we
apply
found
that
it
to
because we
something else?
asked Hannah to Google it. So literally, that's what we did. So in this case, they will not. Technically, you are responsible for being able to find the moment of inertia for regular objects, spherically symmetric objects such as a solid sphere, a solid cylinder, a rod about its center, and so on. You are not going to have to do that because there's just no place for that. But the integral is relatively straightforward. If you do that, you get 2/5 mr squared. Yeah. The
Okay.
one thing that you do have to be aware of is the parallel axis theorem. And I do want to review that here. This actually is a good moment just to talk about that because it fits into that question. So parallel axis theorem. So right now we said, okay, we got that sphere, right? And we're rotating it about its center, right? And we said, in this case, I is equal to 2/5 mr squared. Okay, so what if I, instead of doing this way, I actually decided to make this thing rotate about an axis that is parallel to this axis I was going to make it rotate about. And in this case, I was rotating, I could, for example, make it rotate about this axis, right? But now, because I'm a crazy, oh, you cannot see that at all. So here's my axis in blue. Now, if I were going to be like a cartoon weightlifter, right? In cartoons, they always have them attached to kind of like one of these sticks, and there's like another one over there, yeah? Yeah? You picture that?
Mm-hmm.
Okay. And now I'm going to rotate it about this one here. Okay, so instead of taking my hand and just rotating it like this, right? I'm going to take the whole thing and do these go together? I'm not sure. Okay, hang on a second. Okay, I need something longer. Okay, there it is. Close enough. Okay, so here, so now we're going to take the sphere, attach it to the end, and then rotate it like this. And you kind of already imagine with this big old mass stuck on the end, this is going to be hard to rotate because I have to move it this long distance. Okay, so if we now rotate something that we know the moment of inertia about its center of mass axis, but we rotate it about some axis that is L away, okay, then we just add ml squared to the moment of inertia, and then we have the new moment of inertia. So just add ml squared, the distance between the axis through the center of mass, and the new axis. And that's something they could ask. So if they gave you, you could even be asked to calculate this. This would actually work, right, on the test on Monday. They say, we've got a sphere with a moment of inertia. They could even tell you the value, right? They could say it's 7.3 kilogram meters per squared or something like that. And we're going to rotate it like some crazy cartoon weightlifter about this axis that has a distance of 2 meters or 1 meter or whatever, then find its new moment of inertia about that axis, right? But all you need to do is add ml squared to the original moment of inertia, and you're good to go. And vice versa, it works, of course, too. If you know the moment of inertia about this axis, you can find the moment of inertia about the center of mass by subtracting ml squared.
Is the other weight required, or can it also just be like a stick with a weight on the end?
It could just be a stick. So in this situation, if you were actually going to ask what's the total moment of inertia for this crazy cartoon weightlifter piece of equipment, you would of course have the left sphere a distance L away, and then the right sphere would add its moment of inertia about that axis as well. But we were just talking about how to find the moment of inertia of the left sphere about that point. Yeah, you're right. I mean, I drew it in because just to make sure like that's the kind of device it is. So what we would find here is just the moment of inertia of the sphere about an axis that goes here through that center of that rod, for example.
Okay.
Okay, so let's take a look at part D, that we did that. A second snowball with the same radius is packed so that it is more dense than the original rolls down the same roof. Will the angular speed at the end of the incline for the new snowball be greater than, less than, or equal to the original ball? So let's take a look. Does it have the same radius?
Yes.
Is it being dropped from the same height?
Yes.
Does it have the same mass?
Yes.
No.
No? Oh, I thought it
It's
was just.
packed denser, so it has more mass.
Oh, okay. Sorry.
Okay, but that's okay. That's where they want you to get trapped, and I think we might have. Because it has bigger mass, what's going to happen to the angular velocity at the bottom?
Gonna increase?
Good guess, but take a look at the relationship.
Radius.
Isn't it just going to stay the same because the angular velocity is the same? Because they didn't change.
It didn't change. So omega depends on g, and it's still on Earth. Depends on the height difference, same height difference. Depends on the radius, still the same. Does not depend on the mass. So increasing the mass will not matter. It will have the same angular velocity at the bottom. So the mass does not matter. It only matters the radius. So larger radius will cause a larger relative angular velocity at the bottom. And of course, if the angular velocity at the bottom is bigger, they don't ask this, right? What you found here, what does that tell you? And you probably remember this if you did this experiment. Who wins, the big marble or the little marble? On the Murmelbahn, yeah? You've had this experience?
The small
Okay.
one?
Deprived
The radius
childhood,
is smaller?
clearly. What's that?
Would it be the smaller one since the radius is smaller?
The smaller radius means it is having a bigger omega. And if it has a bigger omega, it has a bigger v. So all through the process, the smaller sphere is moving faster. Okay, so the smaller sphere wins the race. Does this match your experience? Does nobody did this? You didn't have a
I just don't
Murmelbahn?
When I was 5, I used to play with them a lot.
Oh, you
just show
did?
up at a
You
teacher and
did?
like school the kids on which one's faster.
Exactly. Exactly. You know what you're doing now. They might be like, the falling rate does not depend on the mass. Like, yeah, it does. For something that's rotating. Yeah. Anyway, don't do that with elementary school children. It's not nice. I'm just kidding. Okay, and that I think brings us to the end of the problem, doesn't it? Yeah, and then we could explain it based on the relationship, and then we would be good. Okay, so I think we made it through that problem pretty well. Okay. Yeah, they did not ask that. I think that would have been a great at part F, and actually a little more interesting than the question they asked, but oh well. Anyway, we got everything right. We got a good grade on this. I feel pretty good. I'm gonna stop the recording.